left around the time of Brexit and moved most of my activities to Germany. But I'm still part-time here, and it's a great pleasure to be back and see the people for real, and even the buildings, you know. Anyway, let's make this interactive. If there's anything you find interesting, then please do ask. If it's boring, you just give me signals to speed up. And then we can get the maximum benefit out of this. Okay. So in the spirit of reproducibility, the slides are available, so you can reproduce the talk in your own time, and you don't need to take any minutes should you be so desperate to capture information. Maybe that's expecting too much. I'll give a bit of an introduction about what I think reproducibility is, show some examples where the work was not reproducible, make a few suggestions how we could do better, and then close. And if we are overrunning because we had a good discussion, then I'll just chop off some material at the end. And I can sense from some of the discussions that go on that at least in parts very well skilled already. But imagine you write a paper and you use Origin or something to do the data analysis, and then perhaps you want to use Excel to plot the data, so you have this multi-stage thing where you use the mouse to arrange your plot. And then in the paper we would write, figure 1 shows the data we analyzed with Origin, and then you've said which software you have used. And the question then is this reproducible? Could we do it again a week later, a year later, or could somebody else do it? And that's the question for today. We'd like to get to a position where if we publish a result, we can reproduce the same findings at a later period, and also somebody else should be able to do that. So you could say, okay, using a package like Excel, where I have to use the mouse, unless I'm extremely skilled, to do things makes it very hard to track what I've been doing. So maybe I can script this. That's better, but you can still have questions. So imagine I have a MATLAB file with this name, because you know, I need to remember what changes are implemented in that. And that creates a figure called gradeplot.pdf, which is then submitted to the journal. But I may still not be sure whether I have to copy the data from this folder or from that folder so that this script reads the right data set. Can happen. I don't know if that's familiar at all. So then there are people who have made a career out of talking about reproducibility, and they have issued a survey of scientists. This is from 2016. And they have asked people, have you failed to reproduce an experiment? And yes, people say, yes, we have. So here's 90%. So nearly 90% of all chemists have tried to repeat something that somebody else has done, and they couldn't do this. If they try to repeat their own experiments, it's not so much better. We're still looking at 65%. So people in the survey said that 65% of them have experienced a situation where they could not reproduce what they have done before. And that's, of course, not ideal. For some reason, the other disciplines are less honest or better organized. This we don't know. Or perhaps their science is just easier. Okay, let's approach this more formally. When do we call a result reproducible? And well, the scenario is that one group publishes the result and another group can reproduce that result based on the information given with that publication. That's what we like to achieve. This is from the same paper we had before. Many people say we have a problem with reproducibility in science, which is not ideal. Why does this matter at all? Why do I say this is what we'd like to achieve? There are multiple reasons. One of them is that the scientific method is based on reproducibility. It's the whole idea of us understanding things and advancing the frontier of knowledge. You know, if what you find and discover cannot be reproduced, then it's perhaps not real. That's the second point. If your publication result is not reproducible, then we cannot be sure whether it's just described badly or perhaps it's incorrect. And I had a long discussion at the European X-ray free electron laser, where I would try to introduce more reproducible practices. And I talked to one of the leading scientists, and I didn't expect that anybody was supportive, because generally this involves more work. And to my surprise, that scientist said, actually, I like the idea, because when we publish all of the data and the details, then nobody will question that my results are real. Which was a perspective I hadn't seen so far, that you publish something and people perhaps at a conference or so say, oh, I don't believe that anyway. And if you can reproduce it easily, then you may have a stronger point there. And then the third point, which personally I think is quite important, is that if research work is easily reproducible, you can also use it again easily. And as a, say, as a PhD student or as a postdoc starting a project, you would typically start from work that others have done, could be in the same group, could be somewhere else, and maybe you spend the first 6 months, first year, the first 2 years to get to the same results that have been achieved before. If it wouldn't cost you 2 years because you wouldn't have to rewrite the relevant software, have access to all the data, you could spend those maybe 1.5 years of those 2 years doing new things, which would be fantastic. So I think if we had more reproducible results, we would also make faster progress. I want to warn that in different communities across the planet, people use different terms for reproducibility and also mean different things. So I'm using reproducibility here in the sense of that we have an experiment which should be carried out by a different team of people using the same experiment or software, and then I call it reproducible. That is the kind of scenario that I try to describe. You could differentiate this and say, let's worry about, can the same team, can the same people repeat what they've done before? And then in this nomenclature, that would be called repeatability. Or you could also ask, can I get to the same insight using a different experiment? That's a different kind of validation of the work. But we'll see later that nature journals, for example, use this term in the meaning that I mean with reproducibility. So different terms are being used. And papers have been published about this. So you can be specific if it's needed. So here's another reason why we should worry about reproducibility, and that is that publishers have started to discover that this is important. So this is quoted from the Nature's editorial policies, and says that it's important anything you publish should be replicable, and that's the reproducible, just a different interpretation of it. And therefore, authors are required to make materials, data, code, and associated protocols promptly available to readers. Protocol here means what things have you done in which order. Do the experiment, do the data analysis. That's my recipe, my protocol. And so that means if you publish something in Nature, somebody else reads it, has an interest in that, they can contact you and say, please explain this to me, and you're obliged to make all of the information available. If after publication, the readers of your article encounter a refusal by the author or don't get the necessary data, then you can contact the journal and can say to the chief editor, this is not good. And then in the worst case, they will publish a correction to the paper that says this work cannot be reproduced. And this is already in force. So even if we don't care about the scientific principles, for one's own career, if you intend to publish with Nature, then it's a good idea to have all the data available, to be able to respond to the comments from your readers. It also means if you have a competitor you really don't like, you say you want to reproduce their work. That'll cause headaches, because that's not so easy. Okay, and Nature is in parts quite technical about this. This is about what they expect in terms of software, and they are familiar with Git and GitHub and things. So, okay. Last bit of the introduction, why is it difficult to achieve this reproducibility? And I just want to focus on one aspect that in theory, we have an idea. This could be the project of the PhD. We do an experiment or simulation. We've got some other data. We post-process this in some way. We create a figure. We understand something, and we publish. That's a nice linear workflow, and that's perhaps how you would describe it in a paper. In reality, of course, it doesn't work quite like that. Something doesn't work, you need to go back, you get to here, you realize actually, we need to do that again because something wasn't shut off, or you find the overall idea was bad and you start again. So you have this iterative cycle of finding out more things which can extend over many years. Nevertheless, at the end, you need to sell this as a linear story. And sometimes it's hard to keep track of which data set you have used for which analysis. All of this can be done if you're very organized and you have a proper logbook. But it's hard, and often it's not done. Okay. Let me move on to the next section of some not so reproducible examples. This one is somewhat famous in that community. I don't know if you have heard of this paper before. It's published by two professors at MIT, I think, Reinhart and Rogoff, and they were looking at public finances in terms of public debt, and they basically concluded that you must save money to make the economy better. And this was used by various governments to justify their budgeting decisions. And what they have done is that they used Excel, pretty much like I described on the first slide. And there was a master student who tried to reproduce this work. And he couldn't. And then, or maybe it was she, I'm not even sure. And that master student then contacted the authors and said, I'd like to reproduce their work. And they very kindly sent an Excel spreadsheet, which they used. This is great, they still had the data. And in the analysis, they found that when they tried to compute a sum and they marked the fields and they dragged down the cross in the lower right corner of the cell, they didn't drag far enough and they only included 15 out of the 20 countries. So they left out 5 rich countries, and based on that, they basically got the wrong numbers. And so perhaps people had to starve because these guys got their numbers wrong. Unfortunate. Second example, paper from 2001, published in Science, which was followed by a retraction of the same paper in 2006, where people made a mistake in the analysis of some data. In the same edition of Science, there was an article about this problem, so that's quite interesting. There's a self-reflection about this. And in the article, we can learn that they say 2 columns of data were flipped, maybe matrix transposed, who knows, and as a result, everything was wrong, which was concluded from that, and so were the publications. And the lead author said they traced the mixer back to the analysis program, which he says he inherited from another lab. So I got a piece of code, which I've used, which gave fantastic results, only they were wrong. And it took me 5 years to find out. But it's good they found out. I mean, this is already positive things. Both of the examples I mentioned are success stories in the sense that we have discovered the error. And we also have found the source of it. And the problem has been reported to the public. Papers have been withdrawn, or at least there has been a discussion. Of course, it would have been better if it hadn't taken so long. Okay, last problem I want to touch on is a paper that emerged from my own PhD work at this university. And last author has died, sadly, in the meantime. And the other one I know is at an away day today, so I can speak freely. And this was published over 20 years ago. It's a computer simulation, a bit like a molecular dynamics simulation, but taken from a context of superconductivity. And there are some equations in the paper. There's actually a lot more embedded knowledge in the people using those equations to fully describe this. And the main result of this paper was this kind of phase diagram. You can see by the quality of the plot that this is quite old. In any case, for every point in this parameter space, many simulations need to be run and they need to be post-processed, and then you can create this diagram. And I'm pretty sure this paper is also not reproducible. And that's at least in parts because lots of computer code has been written for this, which was not published, and we used many CPU hours. And we didn't describe in detail how we did that. So essentially, one would need to start from scratch if we want to check that this is correct, which will take another 2 years or so. And what is missing? Well, ideally, one would have the simulation source code. It would be good to know how from the output of the simulation I get to the numbers and this phase diagram, in which order, which commands are executed. Have there been any configuration files that should be kept? Many runs have been computed. Perhaps not all were used in the final analysis. That's also an important information. And then strictly, you can also worry about how was this compiled, which version of the compiler was used, which third-party libraries did I use. They all could contain mistakes and errors. So if the overall result isn't correct, one could trace it back to this rather than the physics being wrong. That would also be useful to know. And why is that not reproducible at the time? Well, firstly, nobody really cared about sharing any data or code. That was my impression as a PhD student, at least. There was also no obvious place. Things like GitHub didn't exist. Perhaps we were afraid to show our software to the public. Maybe it's not written nicely. Who knows? We're, after all, not computer scientists, but natural scientists. And of course, also, after having invested all this work, somebody else may take the software and make their own career based on that. Also a concern. In the publication that I mentioned earlier, there was also the question, what reasons people have to produce non-reproducible results? And they mentioned fraud. Okay, right? If you want to send a result that is just not true, then of course it's not reproducible. Okay, didn't come to my mind, but apparently. Selective reporting, I think that has to do with the data selection. I may have 20 results. If I just pick the 3 I like and describe those, I get different result than if I truly average over all. Okay, rest is not so new. So let's look forward rather than be pessimistic or sarcastic. I want to start by saying that I want to focus on computational reproducibility. So this is assuming even if you do an experiment, we have the data in digitized form. And then I propose that we consider a kind of workflow that may only be applicable in parts, that you start from perhaps a configuration file for a simulation or a sample on which you conduct some experiment or which you've grown before. And then you go through this process to produce some more data. And that could be like large data sets, depending on what methods you use. Then perhaps you reduce these data sets by extracting some more meaningful numbers. And then you may have another step where you do something interesting with them, or you just create the figures that you use in the publication. Just as a schematic representation of how we work through a scientific study. And what do we want to achieve? We would like to have this reproducible, which means in the best case, we keep all of these data files and we keep all of the software that has to do with these steps. And I said already before what the things are that one needs to look out for. And we also need to remember the protocol. So, which configuration file has been run with which simulation, with which extra switches, where you say, run this in parallel or use this hardware optimization, and so on. So how can we get there? And I want to touch on 4 different ingredients that you need to track your files. I mentioned version control. You need to deposit the data somewhere on some research data repository so that it's publicly available and lasts there. For the recording of the protocol, I suggest that we automate everything we can, and some people find Jupyter Notebooks useful. And then the last requirement is that in addition to archiving all of that, we also should be able to recreate the software environment in which this can be executed, which isn't actually so easy. And if you've seen all of that before, then this is a good moment to go or get your laptop out and write a paper yourself. Okay, so I guess people are familiar with Git. No need to talk through that. This is what Git is. It avoids file names like these, where people try to do version control through the file system. You can use Git to track configuration file software. But for practical reasons, one could also save a small data file in the Git repository. It's quite forgiving. We can use public services to make those publicly accessible. Although if you put data on GitHub, then there's a danger that Microsoft owning GitHub at the moment may decide to shut it down or charge for it or make your data disappear. So if you want it to be reproducible, it's good to take that repository and archive it in an official place. For example, Zenodo is a service that offers this. Second point is that we need to deposit our actual research data somewhere. And Zenodo is one example. If you have a small data set, that works nicely. Southampton has its own data sharing service with this URL. There are also many domain-specific data repositories, and there is an initiative to gather those in the registry of research data repositories. This is R to the power of 3. What a name. So that's the URL here. And so it could be that for a particular domain you work in, there is actually a central repository where people tend to put their code. There are situations where a data set is too large to deposit. These are synchrotrons and Röntgen lasers, which can produce data sets of a petabyte per week. For example, you do an experiment for a week, you have a petabyte of data. Nobody wants to take that home or publish it somewhere. Typically, in that case, those organizations offer to host the data and make it publicly available. So that's the landscape within one should be able to find a place for your data. I mentioned Zenodo already. It's limited to smallish data sets. It's run by CERN. It seems to probably exist for the next 20 years at least, which is good. And has a good connection to GitHub where you can easily push your Git repository there, and it copies over the authors who have contributed to that automatically populated in the Zenodo metadata files, and you get a digital object identifier which you can cite in your publication. You can say, for this paper, the necessary software is published at this location. Okay, that covers the first 2 points here. Are there any questions, or perhaps you have a good idea? Yeah.
It's a very quick one here. You talked about Zenodo, and you say Zenodo is going to be available for 20 years. 20 years sounds like a long time, but it's nothing. What happened in 100 years? I mean, today we can find papers from 100 years ago from leading early scientists. Okay, they're not very reproducible, but at least we have these papers. If code and data are not if they are so important for our current research, how do we make sure it lasts more than 20 years? In 20 years' time, maybe Python will have disappeared.
Maybe, what is the speed?
Python.
Yes, indeed, that's also a good question. Yes, Fortran will always survive. Absolutely, yes. For the benefit of the remote audience, the question was about a 20-year lifetime isn't actually very long. That's true. In practical terms, I would imagine in 20 years, data sets of 50 gigabytes is not so large that it's easy to just keep it going somehow. But of course, nobody knows. Also, the 20 years are not an official statement. I think that was just a guesstimate. Often people say, if you keep your data for 10 years, it's already pretty good. Not sure that's the right attitude, but so the 20 years here are pretty good. Perhaps it should be better, but that's all we have at the moment. Maybe the university's repository is better, but it may change over time. Okay, good point. All right, recording the protocol. How did we do things in which order? We had this diagram before, and in our data repository with the publication, we should explain how we proceeded. And for example, you could have a readme.txt file in which you say, first we take the sample and then we put it into the device and do the measurements. If it's a process that can be computer controlled, then ideally you have a script that does all of these things, or a number of scripts, or a makefile, or something where you can issue a command and then all the necessary steps are being executed. That's the ultimate answer, independent of the language and the tools you use. If you can do that, if the machine can repeat the process, then it is reproducible. And the trick here is that when you describe how to do something, then you often assume that people know what you know, and you don't spell everything out. At least that's what I do, and it's often what happens. So automatic execution is the way to go. Now, many people say the Jupyter Notebook helps them with this. And can I just ask who knows about the Jupyter Notebook? Okay, fantastic, very good. So no, nothing to say. That's the Jupyter Notebook. You know what it looks like. And so there is a suggestion that the use of Jupyter Notebooks can help with reproducible science for various reasons. One is that when you direct your analysis from the notebook, you essentially have a long script with intermediate checkpoints. And if you make sure before you save this, perhaps you restart the kernel, run through it again, so you can be sure it's all in the right order. If that works, then you have already this automatic recipe of repeating what you've done. And that's half of the game. It's particularly good if you use it anyway, because that means you don't need to change the way you work. I mean, nobody is keen to do any more work to make your results reproducible, because we have other things to worry about. So if you can exploit a tool that you don't mind using, or which perhaps is actually useful, then that's great. And there's also a growing ecosystem around the Jupyter project, which in parts will help with the reproducibility. And then what you could do is that we have a publication. Here's an example. And with that, you can publish, for example, a Jupyter Notebook per figure. And let me just try to jump to this. This web page here. So this is a repository on GitHub that was published together with a paper. It's a copy of it is on Zenodo. So if GitHub disappears, you can still get to it. It refers to the original paper. And in there is an organization of subdirectory of notebooks. And then every important figure in this paper has its own notebook. And if we look at this is a static HTML rendering that GitHub provides for us based on this notebook. And at the very end of that, it shows the figure that is included in the paper. That's one thing one can do. It needs a little bit of discipline at the moment when you create a paper, but it's not so hard, and then you can publish it this way. Conceptually, what in the example I've just shown, what has happened there is that there was some simulation work, and then this bit shown in gray here has been made reproducible through this Git repository. So only those kind of post-processed files are included, and then the necessary steps to create figures in the paper are in there. It's not perfect. It would be better if all of that would be reproducible as well, but it's a start. So that's one thing we can do about recording the protocol. And then the last bit I want to mention is that this is all very well, but if you actually want to repeat this, you also need to have the software to repeat it. And whether we use a script to call Perl or R or whatever, or we use a notebook to call R or Julia or Python, in any case, we need to install Python or Julia or R and the right libraries. And sometimes even more, sometimes you use something you need to compile, maybe something written in Fortran that needs exe and Trilinos and ScalaPack and HDF5 with MPI, but NetCDF without MPI because they're incompatible, and it's complicated. And if we cannot recreate this setup of compiled tools, we cannot repeat what has been done before. So it's easy to say, yeah, I just record the versions. But in practice, if you really want to reproduce it, it's hard to achieve that. And because so for a long time, I thought I'm behaving like an idiot when I look on some HPC machine and I can't compile a simple library. It said on the web page, you download this, you run configure, you run make, and then it doesn't work. And a long time later, I found out it's actually hard. It wasn't just me being stupid. People find it is a hard problem. And the various approaches to simplifying the packaging of software. For HPC, there's Spec and Easy Build. Nix is the package managing of NixOS, which actually has been invented with the purpose of being reproducible. I've only come across this recently. What you can do, of course, is that you create a virtual machine or a container. We're familiar with containers. Install the right software in that environment. That's pretty good because I need to have a machine executable script to create this environment. And then I have captured the protocol of compiling those libraries and the software. And that is what has been done in these publications, for example. So here a Docker container has been created in which the simulations can be executed. And then, as in the example before, Jupyter Notebooks are used to orchestrate this process. So when you check this out, there is a make file, and there's a Docker file, and there's also a binary Docker image somewhere. So you can download that Docker image if you have an x86 machine in which you can host the Docker, so it's not a problem. And you can type make, and then you wait a month or so, and it reruns all the simulations that were necessary, but it can be done. And then you can execute the notebooks that create the figures from these results. That's not bad. Keeping the Docker file is nice because you can then see what is inside the container. But it's also not perfect because you will think, okay, I take the Docker file, I can recreate the container, as in Docker build or whatever the command is. But that then likes to fetch data from the internet, like Python, and perhaps it's not there anymore in 2000 years. So there are also limits to that long-term reproducibility. But if we can sort out the next year and the next 10 years, then it's a good start. The last thing I want to mention is a binder. Binder is a project that has been adopted by Project Jupyter. And perhaps we just try to do this interactively and see what happens. So this was the repository hosted on GitHub that contains all these notebooks for the figures. And here is a launch binder button, which will just take us to a URL that is so small that we can't read it. But let me click on it, and with a bit of luck, it's then displayed up there, which is still small. But it's calling a URL that starts with mybinder.org. This is a public service that runs this binder software. And it gets extra information in here. It gets the GitHub author, GitHub login, Max Albert, and the repository name. And then what Binder does is that it clones that Git repository, and it builds a Docker container locally somewhere in the cloud. So locally is in the cloud, locally to Binder. And it searches through this repository for any hints as to what software is needed. And so here it will find environment.yaml, which is a specification for Conda. So then Binder knows, okay, we need to use Conda. It installs Conda. It takes that environment to create a Conda environment according to what's needed in there. It will then also install a Jupyter Notebook server inside this container, and then connect that server with the browser of the person who has clicked on this button. So I don't know if we are overwhelming Binder. This is not a good sign. Because if it hasn't even started to build this container, then that may take a long time. But we can carry on with the slides and later come back to this. I have a less demanding example, but it's perhaps also good to talk about Binder and my Binder service in a moment. Okay, so this just summarizes what I said. There is this my Binder service where some kind people provide to us these cloud computing resources. And the manpower to run the my Binder service, or the person power, comes from volunteers, many from Project Jupyter and some others. And the computing resources come from sponsors like Google and the Alan Turing Institute and OVF and a research organization in Germany. They all offer part of their HPC facilities or compute resources to be used for this Binder service. Okay, that looks pretty bad. I haven't seen that in a long time. I just, click the URL again and move on. Okay, so I was going to show you a different example where the software requirements are a bit easier. We can fall back to that if the other one doesn't work. I'll start with the summary and we can have a look later if that may come together or not. So what did I suggest we could be doing towards better reproducibility? While we do the research, we should archive all the bits and pieces that we need, use version control, make sure we remember what we've done. And the trick here is to do things automatically. And also to remember what software requirements we have. At the time of publication, we need to make that data accessible and we should publish it together with the paper. So you would perhaps submit the manuscript, and in the manuscript you say details on the detailed workings are available here. Then you cite yourself, you cite the DOI from perhaps the Zenodo archive or perhaps the university's own archive, which should be persistent. And then they're in good shape. And for some people, Jupyter Notebooks are a nice way to realize this. And this feature with the binder service, if it then works, allows you to immediately, within a few minutes, jump into this environment where you can re-execute at least the computational steps of that publication, which is very nice when it works. And another thing worth mentioning perhaps is that the binder looks for common standards or software specifications. So it understands the conda, understands the Python's requirements, .txt, understands install for R and other languages. So it sits on top of existing standards, which is always good because then we don't need to invent a new one. And if you design your data archive well, even if you don't think about binder, it could be that it automatically can provide the right software environment. Things I didn't talk about, if you need a GPU or a large HPC cluster, you have other problems. Your data sets may be too large. I mentioned that. I mentioned difficulties with the Docker containers. We still need an x86 machine. We may need the internet to build a container file. We didn't talk about motivations to make your work reproducible. And they're not great at the moment because we measure people's performance in, well, mostly publications. And nobody is given any credit for making reproducible publications. Or in fact, to create outputs that help others, which could be your competitors. There's really no incentive to do that often, which is unfortunate. So, that would be good to change. If you apply for a promotion and you say, I have only 3 papers, but based on my other data sets, people have published 30 Nature papers, it's not going to get you the promotion. I wish it would. It might also help if we integrate basic computational skills in our research degrees. This has started, but I think more could be done. And I think we should also feel more strongly that it's not bad if you show all of your workings and people discover mistakes. I mean, of course, that doesn't feel great, but it's even worse if it takes 20 years for somebody to do that, and perhaps people have died along the way because they trusted your results. And I don't think that's very deeply embedded in our culture yet. I didn't talk about problems if your data is confidential for some reason, or if you need to use commercial software or closed software, then it's also hard to reproduce those results. If it's just commercial, then you could record which version it is, and you could say if somebody really wants to reproduce that, they need to buy it. And this is the version. But whether that company will still sell it to you in 10 years' time in that version, this is questionable. So if anything, that would suggest try to use open source if you can. So in summary, reproducibility matters. It enables better reusability. Let's not strive for perfection. It's very hard. every little bit helps. In terms of practical ideas, archive everything you can, automate, use open source tools, and also if you can make your own tools open source, which will help with people improving them or finding mistakes in them, which is really great, with unpaid people to correct your mistakes. And we all make mistakes. It's just a question of who discovers them and when. Okay, there's some papers here, and I need to thank the funders, and then I want to close and invite questions.